There is a number I want to give you tonight, but I'm not going to give it to you yet because numbers by themselves do nothing. You can hear the number, you can repeat it, you can write it down and feel absolutely nothing because the human brain did not evolve to feel large numbers. It evolved to navigate a savanna, to judge distances of a few hundred meters, to track the movement of animals, to remember faces, to understand the difference between one fruit and two fruits. The brain is extraordinarily good at these things. But large numbers, truly large numbers, the brain simply flattens them. A million, a billion, a trillion, they all feel roughly the same. Big, just big. So tonight, I don't want to give you numbers. Not yet. I want to give you something else first. I want to give you a feeling, the feeling of genuinely trying to understand how large things are and what happens to a mind when it tries. Because something does happen, something shifts, something in how you hold the world, something in how the ordinary concerns of an ordinary day sit inside you. And I think that shift, that particular quiet, cosmic shift is worth pursuing. Even here, even now, even in the dark, even at the edge of sleep. So settle in, let your body go heavy, and come with me. We are going to try to understand how big the universe is, not compared to a ruler, compared to our home, compared to the Milky Way, the only galaxy we've ever known, and then we will see what that comparison does to us. Part 1, Home First, understanding the Milky Way before we leave it. Before we can understand how big the universe is, before the comparison means anything, we need to understand what we are comparing it to. We need to understand the Milky Way, not as a fact, not as a statistic, as a place, as a home. Go outside on a dark night, not in a city. Find somewhere with no artificial light. A field, a mountain, a desert, the ocean, anywhere the sky is truly dark. And look up. If the moon is not up, and if you are far enough from city lights, you will see it. A band of light across the sky, slightly brighter than the rest of the darkness. Diffuse, soft, almost like a cloud that doesn't quite look like a cloud, stretching from horizon to horizon. This is the Milky Way, not a view of the Milky Way from outside. You are inside it. What you are seeing is the accumulated light of billions of stars, stars in the disk of our galaxy, compressed into a band by the simple geometry of your position within the disk. You are looking sideways through the galaxy. The band is the galaxy's disk, seen from within. The bright center toward the constellation Sagittarius is the galactic center, 26,000 light years away. The direction your eye strains toward without knowing why. What does it feel like to look at the Milky Way? I have asked many people this question. The answers vary. Some say peaceful, some say vertiginous, of feeling like the edge of a height, that impulse to step back from something enormous. Some say small, some say connected. All of those are honest answers. All of them are appropriate responses to seeing with naked eyes the galaxy you are inside. The collection of 400 billion stars that constitutes your home, not your street, not your country, not your planet. Your galaxy, the structure, your solar system has been orbiting for 4.6 billion years. The structure that will be orbiting or merged into something else long after the sun is cooled. The Milky Way is approximately 100,000 light years across. Let me try to give that scale some texture. Light travels at approximately 300,000 kilometers per second. In 1 second, light travels the distance from the Earth to the Moon, and then some. In 8 minutes, light travels from the Earth to the Sun about 150 million kilometers. In 4.2 years, light travels from the Sun to the nearest star, Proxima Centauri. In 100,000 years, light crosses the Milky Way from one edge to the other. Our fastest spacecraft, Voyager 1, the most distant human-made object, is traveling at about 17 kilometers per second. At that speed, it would take Voyager 1 approximately 1.7 billion years to cross the Milky Way. Not 1.7 million years, 1.7 billion years. The Milky Way is not a place you can cross. Not with any technology we have. Not with any technology we can seriously imagine. It is the size of something that simply cannot be traversed. And yet, it is our home, and the universe makes it look small. The shape of home. The Milky Way is a barred spiral galaxy, disc-shaped, relatively thin, perhaps 1,000 light years thick in most of the disk, though the disk is warped and not perfectly flat, with a central bulge, a roughly spherical concentration of older, redder stars surrounding the galactic center, perhaps 10,000 light years in diameter, and a bar, a linear structure of stars running through the center from which the spiral arms emerge. Two major arms, the Perseus arm and the Scutum Centaurus arm, and several minor arms and spurs, including the Orion arm, also called the Orion spur, the minor arm in which our solar system resides. We are not in a major arm. We are between arms, in a quiet neighborhood, about 26,000 light years from the center, roughly halfway out, not at the crowded center, not at the sparse outer edge, somewhere in the middle distance, looking inward toward the bright center, looking outward toward the thinning edge, and looking, if we had the instruments, far beyond the edge, to other galaxies, to other worlds, to the universe that contains us, the Milky Way's mass. The Milky Way contains approximately 200 to 400 billion stars. Different estimates give different numbers because much of the galaxy is obscured by dust and because counting stars across 100,000 light years is not a simple task, but the order of magnitude is clear. Hundreds of billions of stars, the total mass of the Milky Way, including its dark matter halo, the invisible envelope of unknown material that surrounds and pervades the galaxy, is estimated at approximately 1.5 trillion times the mass of the Sun, 1.5 trillion solar masses. It is an incomprehensible number, and yet it is home, the only galaxy any living thing, as far as we know, has ever called home. The only galaxy any mind has ever looked up at and tried to understand. One orbit. The solar system orbits the center of the Milky Way. We complete one orbit every 225 to 250 million years. This is sometimes called a cosmic year or galactic year. In 4.6 billion years of existence, the Earth has completed approximately 18 to 20 galactic orbits. Kahdeksantos elapse around the galaxy 100,000 light years across in 4.6 billion years. The last time we were in approximately this position in our galactic orbit, about 230 million years ago, the first dinosaurs had just appeared on Earth. Triassic dinosaurs. The very beginning of the age of dinosaurs. That was one cosmic year ago. One orbit. Everything since the first dinosaur, every species that evolved and went extinct, every mass extinction, every age of mammals, every ice age, the entire history of our genus and species happened in less than one galactic orbit. We are moving through the galaxy. Right now, at 828,000 kilometers per hour, through the dark, going somewhere, always. Part 2, the neighborhood, the local group, The Milky Way is not alone. It belongs to a family, a gravitationally bound group of galaxies called the local group, about 50 to 80 galaxies, depending on how you count, spread across a region roughly 10 million light years across. 10 million light years. Already, the number has jumped by a factor of 100 from the size of the Milky Way. The Milky Way, 100,000 light years. The local group, 10 million light years. 100 Milky Ways laid end to end would cross the local group. And the local group contains about 50 galaxies. We have already, in just the first step outward, expanded the universe by a factor of 100. And this is just the neighborhood. The members, the dominant members of the local group are two spiral galaxies, the Milky Way and the Andromeda Galaxy, formerly known as Messier 31 or M31. Andromeda is the largest galaxy in the local group. It contains approximately 1 trillion stars more than the Milky Way. It spans about 220,000 light years in diameter, roughly twice the diameter of the Milky Way. It is, by most measures, the Milky Way's older and larger sibling. And it is approaching us at approximately 110 kilometers per second. Andromeda is moving toward the Milky Way. In approximately 4.5 billion years, the two galaxies will collide and merge into a new structure that astronomers call Milkomeda or Milkdromeda, a large elliptical galaxy. The product of two spirals becoming one, the lesser members surrounding the two giants are their retinues, dwarf galaxies, small, irregular collections of stars, some containing only a few million stars, some a few billion. The Large Magellanic Cloud, about 30 billion stars, visible to the naked eye from the southern hemisphere, about 160,000 light years away. The Small Magellanic Cloud, a few billion stars, also visible to the naked eye, about 200,000 light years away. Both are satellite galaxies of the Milky Way, orbiting us, gravitationally bound, slowly being torn apart by our gravity. Their stars gradually being incorporated into the Milky Way, consumed. The Milky Way is not just sitting here quietly. It is eating slowly. Then there are the satellite galaxies of Andromeda. Min 32, 110, NGC 147, NGC 185. And beyond the smaller, isolated dwarf galaxies of the local group, Leo I, Leo II, Sculptor, Fornax, Carina, Ursa Minor, Draco, each one a small collection of ancient stars, some of them so faint they were only discovered in recent decades. Some of them the ultra-faint dwarf galaxies containing only a few thousand stars, barely distinguishable from a star cluster. The local group is rich with these small, quiet inhabitants, and for most of them, no living thing has ever looked up from their dark, sparse skies. No planet, perhaps, no biology, just ancient star, orbiting each other, in the dark, crossing the local group. The local group spans 10 million light years. To cross it at the speed of light would take 10 million years. Homo sapiens has existed for about 300,000 years. To cross the local group at the speed of light would take 33 times the entire lifespan of our species. We will never cross it, not with any technology we can build, not in any time that matters to us or our descendants. The local group is our cosmic neighborhood, and it is already so large that it is essentially unreachable. Everything beyond it is, in any practical sense, infinitely far away. And the local group is one tiny corner of what comes next. Part 3, the Virgo supercluster, 1,000 galaxies. Step back further. The local group is not alone either. It is part of something larger, a galaxy cluster, or rather a supercluster, the Virgo supercluster, also called the local supercluster, a gravitationally bound region containing approximately 100 galaxy groups and clusters, with a total of perhaps 1,000 to 2,000 galaxies, spanning approximately 110 million light years. 110 million light years. The local group 10 million light years fits inside the Virgo supercluster 11 times. We have expanded by another factor of 11. At the center of the Virgo supercluster is the Virgo cluster itself, a rich galaxy cluster containing more than 1,300 galaxies, possibly more. The dominant mass concentration of the supercluster, pulling everything else toward it, including our local group, we are falling slowly toward the Virgo cluster, not falling fast enough to be captured. The expansion of the universe is pulling us away faster than the Virgo cluster can pull us in, but falling, aimed at something we will never reach. The Virgo cluster contains some of the most remarkable galaxies known, M27, a giant elliptical galaxy at the center of the cluster, containing perhaps several trillion stars. Its central black hole, the one imaged in 2019 by the Event Horizon Telescope, is 6.5 billion times the mass of the Sun, the most massive black hole in the local supercluster, driving a jet of plasma that extends 5,000 light years into space. Visible in radio and X-ray, a beam of energy shooting from the core of a galaxy. From a black hole we have now photographed. That image, the glowing ring of the black hole's shadow, is one of the most significant images in human history. We took a photograph of a black hole in a galaxy 54 million light years away. The first image of a black hole, Eva, 110 million light years. The Virgo supercluster. Already the number has become uncomfortable. The mind tries to visualize it and cannot. 110 million years of travel at the speed of light. The first mammals appeared on Earth about 66 million years ago. To cross the Virgo supercluster at the speed of light would take almost twice the time since the extinction of the non-avian dinosaurs. The universe has been around for 13.8 billion years. 110 million light years is less than 1% of that time in light travel distance. Less than 1%. And we are already at a scale where the human mind has completely lost its footing, and we are nowhere near done. Laniakea, our true home in the cosmos. In 2014, a team of astronomers led by Brent Tooley at the University of Hawaii published a paper that reframed our understanding of where we are. They used a new method to map the large-scale structure of the universe, tracing the flows of galaxies through space, following the gravitational currents that pull galaxies toward their attractor regions. And what they found was a structure far larger than anyone had previously defined as our home. They called it Laniakea, a Hawaiian word meaning immeasurable heaven. Laniakea is a supercluster of superclusters, a vast, roughly elongated structure containing approximately 100,000 galaxies, with a total mass of approximately 100 million billion solar masses, spanning approximately 520 million light years, 520 million light years. The Milky Way, 100,000 light years, is to Laniakea roughly as a grain of sand is to a city. Not as a grain of sand is to a building. As a grain of sand is to a city. The Milky Way inside Laniakea is essentially a point. Laniakea contains several large superclusters that were previously thought to be separate structures. The Virgo supercluster, our local region, the Hydra Centaurus supercluster, the Pavo Endis supercluster, the Southern supercluster, all of them flowing their galaxy groups and clusters slowly moving through space toward a common gravitational attractor called the Great Attractor. The Great Attractor is a region of enhanced density and gravitational pull located approximately 250 million light years away in the direction of the constellations Centaurus and Norma. It pulls on us. It pulls on thousands of galaxies, all of them flowing toward it, including our local group, including the Milky Way, including you. Right now, as you lie here, you are moving toward the Great Attractor at approximately 600 kilometers per second, not because of the Earth's orbit, not because of the solar system's orbit around the galaxy, but because of the large-scale gravitational flow of the universe, the great tidal pull of the densest region in our cosmic neighborhood, pulling us slowly, the way the tide pulls the ocean, the way gravity pulls everything. For a long time, the Great Attractor was mysterious. It sits behind the zone of avoidance, the region of the sky obscured by the disk of the Milky Way itself. Our own galaxy blocked our view of it. Only when radio and infrared telescopes, which can see through the dust of the galactic disk, were turned in that direction, did we begin to understand what was there. A massive concentration of galaxy clusters, the Norma cluster at its core, thousands of galaxies, drawing everything around them. And even the Great Attractor itself, enormous as it is being pulled towards something even larger. The Shapley supercluster, 650 million light years away. One of the most massive concentrations of matter in the observable universe. Everything is being pulled somewhere. Nothing is stationary. Even at the largest scales, the universe is in motion. Part 5. The observable universe, the edge of everything we can know. Now we arrive at the true question. Not just our galaxy cluster, not just our supercluster, not just Laniakea. The universe, the whole thing, or rather the observable universe, the part we can, in principle, see. Here is why the distinction matters. The universe is expanding. It has been expanding since the Big Bang 13.8 billion years ago, and the expansion is accelerating. This means there is a boundary. Beyond a certain distance, the light from galaxies can never reach us, because the space between us is expanding faster than the light can cross it. Everything beyond that boundary, and there may be an enormous amount of universe beyond it, is forever inaccessible. We cannot see it. We cannot detect it. We cannot communicate with it. It might as well not exist, not because it doesn't, but because it is causally disconnected from us. The observable universe is defined by this horizon, by the farthest distance from which light can have traveled to reach us since the Big Bang. The observable universe has a radius of approximately 46 billion light years. Wait, the universe is 13.8 billion years old. How can we see 46 billion light years away? Shouldn't the farthest we can see be 13.8 billion light years, the distance light could have traveled in 13.8 billion years? This seems obvious, and it is wrong, because space has been expanding while the light was traveling. The light from the most distant objects we can observe, light that left those objects only about 380,000 years after the Big Bang, has been traveling for 13.8 billion years. but the objects that emitted that light were very close to us then. And in the 13.8 billion years since, the expansion of space has carried those objects and the space between us to a distance of about 46 billion light years. The light has been traveling toward us the whole time, but its starting point has moved away from us faster than the light is traveling. The result, the observable universe has a radius of 46 billion light years, a diameter of about 93 billion light years. 93 billion light years. The Milky Way, 100,000 light years. The observable universe, 93 billion light years. The ratio, 930,000 to 1. The observable universe is 930,000 Milky Ways across. In terms of volume, since we are comparing three-dimensional objects, the ratio is even more extreme. The volume of the observable universe is approximately 4 times 10, 80 cubic meters. The volume of the Milky Way, treating it as a cylinder 100,000 light years in diameter and 1,000 light years thick, is approximately 2.5 times 10, 61 cubic meters. The observable universe is roughly 19 times larger in volume than the Milky Way. 10 followed by 19 zeros times larger. A 10 billion times larger volume. I want to just let that sit. Not try to visualize it. Not try to find an analogy. Just let it sit. 10 billion times larger. In volume, the galaxy we live in, to the universe we inhabit, 1 to 10 billion. How many galaxies? The observable universe contains an estimated 2 trillion galaxies. 2,000,000,000,000,000 galaxy. This estimate, revised upward dramatically by a 2016 study, is derived from the Hubble Deep Field images. Long exposure images of apparently empty patches of sky, each one revealing thousands of galaxies in a region of sky smaller than a grain of sand held at arm's length. 2 trillion galaxies, each containing hundreds of billions of stars. The numbers have ceased to be numbers. They are more like signals that something is vastly larger than the mind can hold. The brain receives the signal, and something happens. Not understanding, not visualization, but a kind of opening, a softening of the certainty that the world is the size it appears to be, a glimpse of the actual scale behind the apparent one, a calculation. Let me try a calculation. If the observable universe contains 2 trillion galaxies, and each galaxy contains, on average, 100 billion stars, then the total number of stars in the observable universe is 2 mal 10, 12 Galaxies mal 10, 11 stars per galaxy gleich 2 mal 10, 23 stars, 206 billion stars, 2 stars. To put this in perspective, the estimated number of grains of sand on all the beaches and deserts of Earth is approximately 10, 19 to 10, 20. There are roughly 1,000 to 10,000 times more stars in the observable universe than grains of sand on Earth. The night sky, which seems so full of stars, shows you perhaps 5,000 stars with the naked eye on the darkest night. Page stars out of 206 billion, 0.000000000000000000002%. You are seeing less than nothing, a microscopic fragment, and it still takes your breath away. Part 6, Deep Time and Deep Space. Looking back through the universe. There is something extraordinary about looking at the universe. Something that took me a long time to really appreciate. When you look at a distant galaxy, truly distant, millions or billions of light years away, you are not seeing it as it is. You are seeing it as it was when the light you are receiving actually left that object. The Andromeda galaxy, 2.5 million light years away. The light reaching your eye from Andromeda left it 2.5 million years ago. When you look at Andromeda, you are seeing it as it was when Homo habilis, one of our earliest ancestors, was beginning to shape stone tools on the African savanna, before language, before fire, before any human thought that we would recognize as thought. You are seeing the past 2.5 million years into the past. The Virgo cluster, 54 million light years away. The light from the Virgo cluster left it 54 million years ago. When you look at it, you see a universe 54 million years younger than today. 54 million years ago on Earth, the dinosaurs had been extinct for only 12 million years. The early ancestors of horses, tiny, multi-toed creatures, were just beginning to evolve. The continents were in slightly different positions. The world was warmer than today, and the light that shows you the Virgo cluster left it in that ancient world. Before humans, before mammals had diversified, before most of the species on Earth today existed, the most distant galaxies the James Webb Space Telescope has observed, approximately 13.4 billion light years away. The light from those galaxies left them when the universe was approximately 400 million years old, less than 3% of its current age. When you look at those galaxies, you are looking at the universe in its infancy. The very first galaxies, before most of the stars that exist today were born, before the solar system, before the Earth, before any planet that could have harbored life as we know it, before chemistry had had time to produce the heavy elements needed for rocky planets. Looking at those galaxies, you are looking almost to the beginning, to the edge of the observable universe in time, to the farthest back we can see. The universe is not just big in space, it is deep in time. And the two things, spatial depth and temporal depth, are the same thing. Every meter of distance is also a unit of time elapsed. Every light year is a year of light travel time. The universe is a four-dimensional structure, 3 dimensions of space and 1 of time, all woven together. When you look at the sky, you're looking through all 4 dimensions simultaneously, seeing different distances, seeing different times, the nearby stars, recent, the Andromeda galaxy, 2.5 million years ago, the Virgo cluster, 54 million years ago, the cosmic microwave background, the farthest thing we can see, the afterglow of the Big Bang 13.8 billion years ago. The sky is a time machine, a four-dimensional archive, a record of the entire history of the universe, compressed into the light that falls in your eyes. Part 7, the cosmic microwave background, the oldest light. In 1965, Arno Penzias and Robert Wilson, working at Bell Labs in New Jersey, were trying to map radio emissions from our galaxy. They were using a large, horn-shaped antenna, originally built for satellite communications, and pointing it at the sky. And they kept picking up noise. A faint, uniform microwave signal coming from every direction equally, not from the galaxy, not from any known source. From everywhere, they checked their equipment meticulously. They found pigeons nesting in the antenna and cleaned out the white dielectric material, their polite way of saying pigeon droppings. They had deposited. The noise remained. They eventually learned that a group at Princeton, led by Robert Dick, had predicted exactly this signal, the relic radiation of the Big Bang. Penzias and Wilson had detected the cosmic microwave background, the oldest light in the universe, the afterglow of the creation. They received the Nobel Prize in 1978. The cosmic microwave background, the CMB, is a snapshot of the universe when it was approximately 380,000 years old. At that point, the universe had cooled enough for protons and electrons to combine into neutral hydrogen atoms. Before that moment, the universe was an opaque plasma. Photons could not travel freely because they were constantly scattering off free electrons. After that moment, called recombination, the photons were free. The universe became transparent, and those photons freed at that moment have been traveling ever since. For 13.4 billion years, cooling as the universe expanded, redshifting from visible light into microwaves, until today, when they arrive at our instruments as a faint glow at a temperature of about 2.7 degrees above absolute zero, filling the sky from every direction. The oldest light there is, the CMB, is nearly uniform. The same temperature in every direction, to about 1 part in 100,000, but not perfectly uniform. When we map it with precision, as the Planck satellite has done, we see tiny variations, tiny fluctuations in temperature, 1 part in 100, 000. These fluctuations are the imprint of tiny density variations in the early universe, regions that were fractionally denser than average. And those regions, those tiny seeds, are the origins of everything, of every galaxy, every cluster, every supercluster, every filament of the cosmic web, every star, every planet, every living thing, everything that exists, everything complex, everything structured, everything that has happened since the Big Bang traces its origin to those tiny fluctuations in the cosmic microwave background, to ripples in the hot plasma of the early universe, less than 1 part in 100,000, out of which grew over 13.8 billion years 2 trillion galaxies, 206 billion stars, and somewhere on one rocky planet, around one ordinary star, in one ordinary galaxy, a creature that can look at those ripples and understand what they are. Part 8. The shape of the universe. Is it infinite? Here is a question I find genuinely disturbing. In the best possible way. Is the universe infinite? Not the observable universe, not the part we can see. The whole thing, the actual universe. Is there more universe beyond the observable horizon? And if so, how much more? The honest answer is, we don't know, and may never know. By definition, whatever lies beyond the cosmic horizon cannot send us any information. No light, no signal, no particle, nothing. The causal structure of the universe, the speed of light as an absolute limit, combined with the accelerating expansion, creates a wall we cannot see through. Not with any instrument we can build, not with any technique we can devise. The universe beyond the horizon is, in the deepest physical sense, unknowable. But we can constrain the size of the total universe, not determine it, but constrain it. We can ask, is the universe curved? If the universe has positive curvature like the surface of a sphere, but in 3 dimensions, then it is finite. It curves back on itself. If you travel in a straight line long enough, you return to where you started. The size of such a universe could, in principle, be determined by looking for specific patterns in the CMB. If the universe was small enough, smaller than the observable universe, you would see the same patterns repeated in different directions. The same fluctuations appearing multiple times in the same characteristic pattern from different parts of the sky. We have looked for this. We have not found it, which means either the universe is larger than the observable universe, likely much larger, or it is not positively curved in this way. Current observations suggest the universe is spatially flat, or very close to flat. A flat universe can be infinite. A flat universe can also be finite, but with a complicated topology that doesn't show the simple curvature signatures we have looked for. The flatness measurements from the Planck satellite constrained the total universe to be at least 250 times larger than the observable universe in diameter. At least, that is a lower bound. The total universe could be much, much larger. It could be infinite. Infinity, the word that ends all comparisons, the number beyond all numbers. If the universe is infinite, there are infinite stars, infinite galaxies, infinite planets, infinite arrangements of matter. And by some arguments that make physicists genuinely uncomfortable, an infinite universe would contain infinite copies of every possible configuration of matter, including infinite copies of you lying in infinite rooms, listening to infinite versions of this, each one slightly different or exactly the same. An infinite universe is not just big, it is everything, every possibility, every permutation, infinitely, many times. I don't know if the universe is infinite. No one does. And I have stopped trying to decide how to feel about the possibility, because I don't think feeling is quite the right response to infinity. Infinity is not something you can hold. It is not a thing you can picture. It is a mathematical concept that, when applied to physical reality, produces implications that exceed the capacity of any mind, human or otherwise, to contain. What I can say is this: the universe is at least as large as the observable universe, 93 billion light years across, 2 trillion galaxies, 200 sextillion stars, at least, and that is enough. That is more than enough to put everything in perspective, to make the world feel its actual size. Small, precious, extraordinary in its smallness. Part 9, the scale in your hands, analogies that almost work. I promised at the beginning that I would try to give you a feeling, not just numbers. Let me try some analogies. They will all fail. That is the point. The failure of the analogies is itself informative. The beach ball, imagine the Milky Way is the size of a beach ball, about 30 centimeters across. On that scale, our solar system, 8 light hours across approximately would be about 0.000003 centimeters, too small to see with any microscope, too small to be a molecule. We would be subatomic. The solar system on the scale of the beach ball Milky Way would be essentially invisible. And the entire observable universe on that same scale would be approximately 28 kilometers across, about 28 kilometers, the distance from a city center to its suburbs. The beach ball sits in the city center. The observable universe extends to the suburbs, and our solar system is a point on the beach ball too small to exist. The atom, here is another way to approach it. The ratio of the size of an atom to the size of a human being is roughly 1 to 100 billion. 1 to 100 billion. The ratio of the size of the Milky Way to the size of the observable universe is roughly 1 to 930,000. The Milky Way is to the observable universe roughly as a dime is to a large country, not as an atom is to a human, not as small as that. a dime to a country, that is the relative size of our galaxy. The sand grain, there is a comparison I particularly love. Imagine you are standing on a beach. You pick up a single grain of sand. That grain of sand represents the observable universe. Now imagine the beach, all the beaches on Earth, all the sand on all those beaches, that represents the total universe. If the universe is about 250 times larger in radius than the observable universe, as the lower bound suggests, actually, that comparison undersells it. If the universe is infinite, there is no comparison. But even at 250 times larger in radius, which is a lower bound, a minimum, the ratio in volume is approximately 250 cubed, or about 15 million to 1. The observable universe is 1/15 millionth of the minimum universe. The grain of sand is 1/15 millionth of the beach, and that is the lower bound. The actual universe may be incomparably larger. The analogies fail. They all fail, because the human mind was not built to feel these scales. We evolved for a world measured in meters and kilometers, a world where the horizon is a few kilometers away, where the farthest we might realistically travel is a few thousand kilometers, where the largest thing we ever needed to understand was a mountain, or un océan, or a continent. The universe is not a continent. It is something that has no analog in human experience, no comparison that does it justice. And perhaps that is the most honest thing I can say. The universe is not just large, it is categorically different in scale from anything our minds evolved to process. And the attempt to feel it, the honest, earnest attempt to stretch the mind toward its true scale, is one of the most humbling and quietly wonderful things a human being can do. Part 10, the void, what's between everything. I have been talking about galaxies, but most of the universe is not galaxies. Most of the universe is nothing, or very nearly nothing. The voids. The cosmic web, the large-scale structure of the universe, is made of filaments and nodes. The filaments are long, thread-like structures where galaxies cluster. The nodes are the dense intersections where galaxy clusters form. And between them, taking up the vast majority of the volume of the universe, are voids, regions of space nearly empty of galaxies, nearly empty of ordinary matter, vast dark bubbles. The largest known void in the observable universe is the Boötes void, approximately 330 million light years in diameter. It contains very few galaxies, perhaps 60, compared to the thousands you would expect in a region that size. If the Milky Way were located in the center of the Boötes void, our astronomers in the ancient past would have seen no galaxies at all for most of history. No Andromeda, no local group companions, nothing, just an apparently empty universe, a black sky, until technology good enough to see across the void was developed. Only then would they have discovered that the universe beyond was full of galaxies, that they were in a bubble, a vast, dark bubble. Voids are not truly empty. They contain diffuse gas. Dark matter filaments thread through them. Occasional galaxies exist even there, but they are close to empty. They are the universe's silence, the vast, dark silence that fills most of the space between the luminous threads, and they are enormous, hundreds of millions of light years across, each one, and there are countless voids. The universe's volume is mostly void. The luminous structures we call galaxies, the things that feel like the universe, to us occupy a tiny fraction of its volume, perhaps a few percent, maybe less. The rest is silence. Dark, nearly empty, vast. I sometimes think about what it would be like to travel through a void, not the journey that is impossible, the experience, if you could. You would pass through it without ever seeing another galaxy. Billions of light years of dark, of nearly empty space, of silence so profound that there is no medium for sound and no light to see. Just the faint glow of the cosmic microwave background, the same in every direction, the same as it is everywhere. A monotone signal from the birth of the universe, and the occasional dark matter particle passing through you as they pass through you now. In the void between galaxies, if you were there, the dark matter would be less concentrated. Fewer particles, more emptiness, but still something. The void is not truly nothing. It is almost nothing. And in the universe, almost nothing is still something. Part 11. The first light before the universe had structure. Let me take you further back. Before galaxies, before stars, before any structure at all. To the beginning, to what cosmologists call the Dark Ages. After the CMB was released after recombination, 380,000 years after the Big Bang, the universe went dark. Not the darkness of a room at night, the darkness of a universe without stars. Hydrogen gas, helium gas, drifting, cooling, expanding, dark. For perhaps 150 to 800 million years, the estimates vary, the universe had no stars, no light, no illumination, just the slow collapse of gas under gravity, just the beginning of structure, dark matter halos forming, gas cooling and pooling within them, slowly, over millions of years, building toward the first stars. The first stars, population 3 stars, they are called, were different from any stars that exist today. They formed from almost pure hydrogen and helium, no heavy elements, no carbon, no oxygen, no iron, just the lightest elements. And because there were no heavy elements to help cool the gas, and cool gas collapses more easily into smaller, more moderate stars, the first stars were giants, perhaps hundreds or thousands of times the mass of our sun, blazing with an intensity we cannot easily imagine, pouring out ultraviolet radiation, ionizing the hydrogen around them, beginning the process of reionization, the second great phase transition of the universe, when the Dark Ages ended and the universe became transparent again. Not transparent because the atoms recombined, transparent because the atoms were ionized, stripped of their electrons by the first light. The first stars lived briefly, a few million years, and then they transformed, exploding, scattering their contents, the heavy elements they had forged in their cores, into the gas around them. Carbon, oxygen, neon, magnesium, silicon, elements that had never existed before, seeding the universe, making the next generation of stars possible. Stars that could form planets, planets that could form chemistry, chemistry that could become biology, biology that could become us. The transition from the Dark Ages to the first stars is one of the most dramatic events in cosmic history. The universe went from total darkness, no stars anywhere, no light except the fading CMB, to the first points of nuclear fire, the first stars switching on, the first light since the CMB, the universe illuminating itself for the first time, and we can almost see it. The James Webb Space Telescope is peering into this era, detecting the faint light of some of the very first galaxies, looking at the universe that was only a few 100 million years old, when the first structures were just forming, when the first stars were blazing, the oldest light from the oldest things, still traveling, after 13 billion years. Still arriving, part 12. The future of the universe, where everything is going. We have talked about the universe as it is now, as it was. Let me take you to where it is going. The universe is expanding, notata constanterate, accelerating. The dark energy, the energy of the vacuum itself, is pushing space apart, faster and faster. And this has consequences for the future, for the very long future. In the short term, the next few billion years, not much changes. The galaxies of the local group remain gravitationally bound. The Milky Way and Andromeda collide and merge. The merged galaxy, Milky Way, settles into an elliptical shape. The sun becomes a red giant. The inner planets are consumed. The earth is scorched. Whatever life exists, if any, has long since had to find somewhere else. In the medium term, tens of billions of years, the stars begin to die. The most massive stars are already long dead. The sun-like stars burn out. What remains are the misers, the red dwarfs. Stars so small and so cool that they burn their hydrogen at an almost geological pace. Red dwarfs can live for trillions of years. The age of the universe is 13.8 billion years. Red dwarfs will still be burning when the universe is 1,000 times older than it is now. For the next trillion years, the universe will still have stars, will still have light, will still conceivably have life, but slowly, one by one, even the red dwarfs will exhaust their fuel and go dark. In the far future, after the last star dies, the universe enters what physicists call the degenerate era. No more fusion, no more starlight, just the cold remnants. White dwarfs cooling, fading, becoming black dwarfs as they lose their heat over trillions of years. Neutron stars, incredibly dense, incredibly cold, spinning slowly down. Black holes, the dominant objects of the era, still there, still growing, slowly. As they swallow what little remains, the universe dark, cold, empty, but even black holes are not eternal. Stephen Hawking showed that black holes slowly evaporate, emitting a faint thermal radiation over enormous timescales. The largest black holes, the supermassive ones at the centers of galaxies, will take perhaps 100 years to evaporate. A Google years, far longer than the current age of the universe. And in the final moment of their evaporation, a burst of radiation, and then nothing, or very nearly nothing. The universe in its final state, a cold, dark, essentially featureless expanse, photons of such low energy they barely qualify as light. A few remaining particles drifting in an expanding void. The era physicists call the dark era, the long, quiet, cold ending of everything. And yet, even in the far future, even in the dark era, something might persist. Life, perhaps, not life as we know it, not biological life, but patterns, information, complexity organized into something that processes and responds, and perhaps in some form we cannot imagine experiences. Some physicists have speculated about life in the far future. Life organized around the slow flow of heat between black holes. Life based on the quantum fluctuations of an otherwise cold universe. Life that runs so slowly, metabolizing at 1 thought per trillion years that it is essentially unrecognizable to us. But still, perhaps something, the universe's tendency toward complexity is remarkable. It may not end even as everything else does. Part 13, the question of other universes, beyond the observable, There is a word that physics has arrived at reluctantly, a word that makes some physicists deeply uncomfortable, because it seems to belong to philosophy, or to religion, or to science fiction, not to physics. The word is multiverse. The multiverse, the idea that our universe is not the only universe, that there are many universes, perhaps infinitely many, arises naturally from several independent lines of theoretical reasoning, not as speculation, as a logical consequence of well-supported theories. Inflation, the theory of cosmic inflation, the idea that the universe underwent a period of exponentially rapid expansion in the first tiny fraction of a second, is one of the most successful theories in cosmology. It explains why the universe appears flat, why the CMB is so uniform, why the large-scale structure looks the way it does. The evidence for inflation is strong, but inflation in most of its theoretical formulations does not stop everywhere simultaneously. In most models, inflation is eternal. It continues in other regions of space forever. Bubbles, regions where inflation is stopped and settled into something like our universe form within the eternally inflating background. Each bubble, a universe with its own physical constants, its own laws, its own history. Ours is one bubble. There may be infinitely many others. String theory. String theory, the attempt to unify all the forces and particles of nature into a single framework, predicts an enormous number of possible universes. The landscape of string theory, perhaps 10, 500 possible combinations of physical constants, Shu by 1 followed by 500 zeros, each combination a different universe, with different masses for particles, different strengths of forces, different amounts of dark energy, different physical laws. In most of those universes, nothing interesting happens. The constants are wrong for chemistry, wrong for stable atoms, wrong for stars, wrong for planets, wrong for life. But in a tiny fraction, perhaps the constants happen to permit stars, chemistry, planets, biology, and we inevitably find ourselves in one of those rare universes. Not because our universe was designed for us, but because we could only exist in a universe where the constants permitted our existence. This is the anthropic principle, not a physical theory, a selection effect. The observed universe appears fine-tuned for life, because only in universes that permit life do observers exist to observe the apparent fine-tuning. In all the universes where the constants are wrong, there is no one there to notice. The emptiness goes unobserved. Only the hospitable universes produce observers. Only the observers can ask why the universe is hospitable. I want to be honest about the multiverse. It is speculative. No version of it has been confirmed. No version of it may be confirmable by definition. Other universes are beyond our observational horizon. They may be beyond any possible observational horizon. The multiverse may be science, or it may be at the edge of science, or it may be beyond science, a metaphysical idea that happens to arise from physical reasoning. We do not know. What I can say is that the physicists who work on it are serious people, asking serious questions, following the mathematics where it leads, even when it leads to uncomfortable places. The multiverse is not a fringe idea. It is a serious theoretical possibility, taken seriously by some of the most rigorous minds in physics. And it emerged not by design from attempts to understand the universe we do live in. Part 14. What size does to us the philosophical weight of scale? I want to step back now from the physics from the numbers, from the infinite voids and the 2 trillion galaxies and the 200 sextillion stars, and think about what all of this means, what it does to a mind that really tries to hold it. The most common response when people first truly encounter the scale of the universe is a feeling of smallness, of insignificance, of being tiny and brief and lost in an incomprehensible expanse. I understand that response. It is honest. It is appropriate. The universe is incomprehensibly large, and we are incomprehensibly small in relation to it. But I want to offer another response, not instead of the first one, alongside it, because I think both are true simultaneously. And the tension between them is where the interesting territory lies. Yes, we are small. The Milky Way is 100,000 light years across. The observable universe is 93 billion light years across. We are one species, on one planet, orbiting one star, in one galaxy, among 2 trillion. By the simple arithmetic of scale, we are negligible, less than negligible, essentially invisible, a rounding error in the universe's accounting. And yet, there is something happening here on this planet, around this star, in this galaxy that we have no evidence of happening anywhere else. Awareness, the universe knowing itself through us. Consciousness, the capacity to look out at the 2 trillion galaxies and feel something, to be moved, to wonder, to ask. The universe is vast, but it is also, as far as we know, mostly unconscious. The stars burn without knowing they burn. The galaxies collide without experiencing the collision. The cosmic web forms and evolves in complete silence. No awareness, no experience, just physics, automatics, blind. And then here, on this small rock, in this quiet corner, a pattern of matter complex enough to notice, to feel, to ask why. We are tiny in space, but we may be enormous in rarity. The rarest thing in the universe may not be dark matter, may not be some exotic particle, might not be a supernova or a magnetar or a quasar. The rarest thing in the universe may be consciousness, maybe a mind that looks at all of this and finds it beautiful. Part 15, Fermi's question, where is everyone? If the universe is this large, if there are 2 trillion galaxies, if each galaxy contains hundreds of billions of stars, if many of those stars have planets, if many of those planets are inhabitable zones, if life arose on Earth in a few 100 million years, once conditions were right, then why haven't we found anyone else? This is the Fermi paradox, named for physicist Enrico Fermi, who asked the question over lunch in 1950, where is everybody? The mathematics seem to demand that the universe be full of life. The observations show, at least so far, that it is empty, or at least quiet. We have been listening. SETI, the search for extraterrestrial intelligence, has been scanning the sky for radio signals for over 60 years. We have searched millions of star systems. We have found nothing. Not a señal, not a pattern, not a hint. The universe is silent. Why? The explanations divide into 2 broad categories. We are early, or life is rare. We are early. Perhaps the universe was not hospitable to life until recently. The early universe was poor in heavy elements. The universe needed several generations of stars to cycle through before there was enough carbon and oxygen and iron for rocky planets and biology. Only in the last few billion years has the cosmic chemistry been rich enough for complex life. Perhaps we are among the first complex life to arise. Perhaps civilizations are rare not because life is rare, but because the universe is still young. We are not alone. We are simply early. And in millions of billions of years, as more planets form, as more stars age appropriately, the universe will fill with life. We are the vanguard. Life is rare, or perhaps the opposite. Perhaps life, or complex life, is extraordinarily rare. Perhaps the steps from simple chemistry to the first cell, from single-celled organisms to complex multicellular life, from complex life to intelligence and technology, are each individually so improbable that they almost never all happen in sequence. Perhaps Earth is unusual, not just in having life, but in having this particular sequence of events: the right planet, the right sun, the right moon, the right giant planet as a shield, the right plate tectonics, the right chemistry, the right history of extinctions, catastrophic enough to drive evolution toward complexity, not so catastrophic as to end everything, each step possible, each step unlikely, the cumulative probability vanishingly small. Perhaps we are alone, not because the universe is small, but because the conditions for intelligence are so specific that we are genuinely the first, the only in the observable universe. I do not know which is true. I find myself drawn on different days to different answers. The silence of the sky is genuinely mysterious. Given how vast the universe is, given how old it is, the silence is harder to explain than it might seem. If intelligence arises readily, if the development of technology is a natural consequence of evolution, then by now, some civilization somewhere should have had enough time to spread across a significant portion of the galaxy, to be visible, to leave traces we could detect. The absence of those traces, the great silence, is the Fermi paradox. And it has no consensus resolution. It remains open, one of the most important open questions in science, and one that, if answered, would tell us something profound about our place in the universe. Part 16, the long view, what perspective does. The universe is 93 billion light years across. The Milky Way is 100,000 light years across. The ratio, 930,000 to 1. But here is what I wanted to notice. In a universe 930,000 times larger than our galaxy, in a universe containing 2 trillion galaxies, in a universe that has existed for 13.8 billion years, something happened. Here, in this galaxy, around this star, on this planet, something capable of asking, how big is the universe? Something capable of being moved by the answer. Something that can lie in the dark and feel the weight of the question, and find peace in not knowing everything, and wonder at what it does know. The universe did not have to produce this. It is not obvious that physics leads to chemistry, leads to biology, leads to consciousness. It might not. In most of the universe, it apparently hasn't. The stars burn without knowing, the galaxies spin without caring, the voids extend without feeling. But here, in this corner, something is different. Something is happening. Has been happening for about 600 million years if you count complex multicellular life, for about 66 million years if you count mammals, for about 300,000 years if you count us. And in those 300,000 years, that cosmological eye blink, something extraordinary has happened. We went from caves to telescopes, from stone tools to instruments that can detect the CMB, from trying to understand the weather to trying to understand the Big Bang, from drawing constellations to mapping the cosmic web, from not knowing the Earth was round to knowing the shape of the observable universe, from not knowing other galaxies existed 100 years ago to understanding that there are 2 trillion of them, 300,000 years, in a 13.8 billion year old universe. That is 0.002% of the universe's lifetime. And in that 0.002%, we have learned most of what I have told you tonight. The mind boggles not at the size of the universe, at the speed of understanding, at how fast the 5% figured out what the universe was made of, at how quickly we mapped invisible dark matter, at how rapidly we pushed the observable boundary back to the first light. We are slow by galactic standards, brief by cosmic standards, but we learn fast, and we have barely started part 17, the nearest star, what we cannot reach. Let me bring this back to the intimate scale, the human scale, the scale that matters to us. The nearest star to the sun is Proxima Centauri, 4.24 light years away, a red dwarf, small, dim, long-lived, with at least one planet in its habitable zone, Proxima Centauri b, a rocky planet, perhaps with an ocean, perhaps with conditions for life, 4.24 light years away. Voyager 1, our most distant spacecraft, the farthest humanity has ever sent an object, is traveling at about 17 kilometers per second. At that speed, it would take approximately 70,000 years to reach Proxima Centauri. If it were headed in that direction, it is not 70,000 years. Our species has existed for 300,000 years. A journey to the nearest star would take almost a quarter of our entire species history, with our fastest spacecraft. And Proxima Centauri is the nearest star, 4.24 light years, in a galaxy 100,000 light years across, the nearest neighbor, and we cannot reach it, not in any human lifetime, not in any time scale that matters to civilization, not with any technology we currently have. The stars are unreachable, not difficult, not expensive, unreachable by the laws of physics as we understand them. And yet, we know they're there. We know their temperatures, their ages, their compositions, their distances, their motions. We know whether they have planets. We can detect the atmospheres of those planets. We can measure the molecules in those atmospheres. From here, without going there, without sending anything there, just by analyzing the light that arrives. The light does what we cannot. It travels between stars. It carries information. It tells us what is out there. And we here receive it, read it, understand it. The nearest star is unreachable, but it is not unknowable. The universe is not reachable, but it is not unknowable. We study it from this fixed point, from this planet, from this brief moment, and we have learned extraordinary things. Part 18, the overview effect, what astronauts feel. There is a phenomenon well documented among astronauts. Those who have seen the Earth from space, from the distance of the moon, or from orbit report a consistent experience. A transformation, a shift in perspective that many describe as one of the most profound experiences of their lives. They look at the Earth as small, blue, fragile ball hanging in the blackness of space. No borders, no division, just a planet, whole, alone in an enormous dark, and something changes in them. The concerns of ordinary life, politics, money, conflict, the boundaries between people feel suddenly arbitrary, suddenly small. not unimportant, but small, appropriately scaled against the background of an infinite dark. This is called the overview effect. The astronaut Edgar Mitchell, who walked on the moon in 1971, described looking out at the Earth and the stars and feeling what he called a flash of understanding, a sudden, visceral sense of connection, of the universe being aware of itself through him, of being part of something vast and ancient and alive in a way he had not previously understood. He said he knew in that moment that the universe was in some way conscious, not because he had evidence, but because of what it felt like to see the Earth from space. I am not an astronaut. I have never been to space. I have experienced the overview effect only secondhand, through photographs, through the words of those who have been there. But I believe them because I have felt something like it. Not looking at the Earth from space, but looking at the universe from a dark hillside on a clear night with no artificial light and the Milky Way blazing overhead. And the thought, the real thought, not just the abstraction of what I was actually seeing, the galaxy I live in, from the inside, hundreds of billions of stars, the nearest one 4.24 light years away, and all of them, every single one within my galaxy, within my home, something shifts. The ordinary falls away, not permanently, but for a moment, the perspective is correct. And in the correctness of the perspective, in seeing the actual scale of things, there is something like peace. Part 19, the return, coming back to the room. We have traveled far tonight, from the Milky Way 100,000 light years across, to the local group 10 million light years, to the Virgo supercluster 110 million light years, to Laniakea 520 million light years, to the observable universe 93 billion light years, to the question of what lies beyond, to the possibility of infinity, to the question of other universes, to the silence of the Fermi paradox, to the overview effect, to the extraordinary fact that something here can know all of this. Now let us come back, slowly, without rush, back through the scales, back through the superclusters, back through the galaxy clusters, back through the local group, back into the Milky Way, into the Orion Arm, into the solar system, into the Earth, into the atmosphere, into the city, into the building, into the room, into the body, into the breath. This breath, right now, the breath that is moving through you as you listen, the oxygen entering your lungs, oxygen made in the cores of massive stars, scattered by their transformation, incorporated into the solar nebula, into the early Earth, into the atmosphere, into you. The carbon dioxide leaving the carbon, forged in stellar cores, cycling through the biosphere, through every living thing that has ever breathed on this planet, through you, now, leaving. The breath is part of the universe. You are part of the universe, not separate from it, not small against it. Part of it, the part that can know it. The universe is 93 billion light years across. The Milky Way is 100,000 light years across. The ratio is 930,000 to 1. And somewhere in that ratio, somewhere in the Milky Way, on a rocky planet, in a thin film of atmosphere, a mind is holding this comparison, feeling it, trying to understand it, finding it beautiful, finding it peaceful, finding somehow that the incomprehensible scale of the universe makes the room quieter, makes the breath slower, makes the night feel exactly the right size, large enough to hold everything, quiet enough for sleep. Part 20, the stars you cannot see. What is always there? The stars are there right now. even in daylight, even behind clouds, even in the light-polluted sky of a city. They are there, the same stars, the same galaxy, the same universe, just hidden by the brightness of one nearby star. Our sun, the sun rises. The sky fills with scattered blue light. The stars disappear, not because they have gone, because the atmosphere scatters sunlight so intensely that the sky is bright from every direction. The stars are overwhelmed, drowned in blue, but they are there, waiting as they waited last night, as they will wait tomorrow. The Andromeda Galaxy is out there right now, 2.5 million light years away, moving toward us at 110 kilometers per second, as it has been every day, every night, for all of history. Whether we can see it or not, whether we are looking or not, whether we know it exists or not, the universe does not require our attention to continue. It does not wait for us. It does not care whether we look. It simply is. Continuous, patient, vast, and yet we look. That is the remarkable thing. Not that the universe is there, but that something in it looks and wonders and finds it worth looking at. The universe is 93 billion light years across. And somewhere in it, in this galaxy, on this planet, something is quietly amazed by it. Every night, looking up, trying to understand. Part 21, the deep field, the most important photograph ever taken. In December 1995, the Hubble Space Telescope was pointed at an apparently empty patch of sky, a region selected for its emptiness. No bright stars nearby, no known galaxies, just black sky. The telescope stared at it for 10 consecutive days, 342 separate exposures, each one capturing the faintest possible light. The total exposure, 140 hours. When the image was processed and revealed, astronomers were stunned. The empty patch of sky was not empty. It was full of galaxies, approximately 3,000 galaxies, in a patch of sky so small that if you held a grain of sand at arm's length, the grain would cover it. 3,000 galaxies in a grain of sand's worth of sky. The image was called the Hubble Deep Field. It fundamentally changed our understanding of the universe. Before it, astronomers estimated there might be tens of billions of galaxies in the observable universe. After extrapolating from this one patch to the whole sky, the estimate jumped to hundreds of billions. And later, with better data, to 2 trillion. The universe was full of galaxies, not just the ones we knew about, full, every patch of sky, every direction, full. When I look at the Hubble Deep Field, and I have looked at it many times, something happens that I cannot quite put into words. Each of those 3,000 points of light is an entire galaxy. Each galaxy containing hundreds of billions of stars. Each star potentially with planets. Each planet potentially with chemistry. Some of those galaxies are more than 10 billion light years away. The light I am seeing left them when the universe was less than 4 billion years old, when the Earth did not yet exist, when there was no sun, in a patch of sky the size of a grain of sand. 3,000 of them. The Hubble Ultra Deep Field went deeper. 1 million seconds of total exposure, revealing nearly 10,000 galaxies. Some of them among the most distant objects ever photographed, formed when the universe was only a few 100 million years old. The Webb Deep Field, taken by the James Webb Space Telescope in 2022, went deeper still, revealing galaxies previously invisible, the oldest, most distant structures we have ever seen. the infant universe, the first galaxies, before our galaxy existed, before our star existed, before the Earth existed, photographed from Earth, from the planet they predate. Looking back at the time before our home existed, I don't know how to talk about this without emotion. These images are among the most extraordinary things our civilization has produced. Not because of the technology, not because of the physics, but because of what they represent. Conscious matters looking at the universe it came from. Before the universe had made us, seeing its own past, from its present, through instruments of extraordinary ingenuity. This is what it means to be alive now. In this moment of cosmic history, when the tools exist to see back to the beginning, when we are old enough to understand what we are seeing, young enough to still find it stunning. Part 22, the silence being here. Let me stop talking for a moment. Not literally, I will keep speaking, but let me slow down. Let the space between sentences grow. Let the ideas settle. Because I have given you a great deal tonight, and it is not always useful to have more. Sometimes it is more useful to have less, and space and quiet. You are inside the Milky Way, a galaxy 100,000 light years across. You are on a planet orbiting a star, about 26,000 light years from the galactic center. You are in the Orion Arm, in the local group, in the Virgo supercluster, in Laniakea, in the observable universe, in the universe, at all these scales simultaneously. You are always at all these scales. The scales do not compete. They nest, like Russian dolls, each one inside the next. The room inside the building, inside the city, inside the country, inside the continent, inside the planet, inside the solar system, inside the galaxy, inside the local group, inside Laniakea, inside the observable universe, inside the universe. You are inside all of them, right now, simultaneously, and you are also just here, in this room, in this moment, breathing, at the end of a long journey through scale and time and structure, arriving back at the simplest thing, the breath, the body, the quiet. The universe doesn't need you to understand it to be what it is. It existed for 13.8 billion years before you arrived. It will exist for far longer after. It does not ask anything of you, not comprehension, not appreciation, not even attention. It simply is, and you are simply in it. And right now, that is enough. Part 23. What remains? The facts that matter. Of everything I've told you tonight, all the numbers, all the comparisons, all the scale, what do I want you to carry? Not the number 93 billion. Not the ratio 930,000 to 1, not the 2 trillion galaxies, not any specific fact. What I want you to carry is the feeling that the universe is genuinely, staggeringly, incomprehensibly larger than it appears from here. And that this does not make here less important. It makes here more interesting. We are not the center of the universe. We are not even at the center of our galaxy. We are at the edge of a minor arm of a medium-sized spiral galaxy in a small group within a supercluster, within a larger supercluster, within an observable universe of 2 trillion galaxies. We are nowhere special by every geometric measure. And yet, we are the part that knows this. We are the part that measured the rotation of galaxies and inferred the dark matter, that mapped the CMB and read the early universe, that built telescopes to see back to the first light, that pondered the Fermi paradox, that wondered about other universes, that found the Hubble Deep Field full of galaxies, that felt something looking at it, that built the words to describe what it felt. The universe is 930,000 Milky Ways across, and the Milky Way contains us, the most complex known arrangements of matter, the only known arrangements capable of asking why. We are not nowhere. We are in the Milky Way, and the Milky Way is one of 2 trillion galaxies, and we are in the one that knows it. Part 24, the weight of light, what every photon carries. Every photon that reaches your eye carries a message, not a metaphor, not poetry, literally a message encoded in wavelength, in timing, in polarization, in the Doppler shift of its frequency. The universe is not silent. It is broadcasting constantly from every object, in every direction, an unimaginable flood of information streaming outward. And we here have learned to receive it, to decode it, to read what the universe is saying about itself. When you look at the night sky, you are receiving messages from other stars. Each photon has a story. It was created inside a star in the nuclear reactions at the core or in the churning convective layers near the surface. It fought its way outward through the star's dense interior, bouncing from atom to atom, absorbed and re-emitted, taking thousands of years to travel from the core to the surface. Then it was finally free. It shot outward into space, traveling at the speed of light. For years, for centuries, for thousands of years, until it struck your retina and you saw a point of light, a star, without knowing any of this, without knowing the journey the photon took to reach you. But the photon carries information about that journey. Its wavelength tells you the temperature of the star's surface. The pattern of wavelengths, the spectrum, tells you the chemical composition. The width of the spectral lines tells you the pressure in the stellar atmosphere. The Doppler shift tells you whether the star is moving toward you or away. The variation in brightness over time tells you about stellar rotation, about star spots, about orbiting planets. One photon carries a compressed archive of everything that happened to it, from its creation in the nuclear furnace of a stellar core to the moment it ends its journey in your eye. We have learned to unpack that archive, to reverse engineer the history of a photon from its properties, to look at a point of light and know what it is made of, how hot it is, how far away it is, how it is moving, whether it has planets, what is in the atmosphere of those planets from here, without moving, without sending anything there, just by being patient with the light that arrives. The oldest photons we can receive are from the cosmic microwave background. They were created 380,000 years after the Big Bang, when the universe first became transparent, when matter and radiation decoupled. And those photons, freed 13.8 billion years ago, have been traveling ever since. They arrive at us now as microwaves. Their wavelength stretched enormously by the expansion of space, 1 billion times longer than when they were emitted, but still carrying information about the temperature of the universe at the moment of their release, about the density fluctuations in the early plasma, about the composition of the universe at that first moment of transparency. We can read it. We built instruments sensitive enough, and we pointed them at the sky, and we listened. And the universe told us everything it could about its own birth, through light that had been traveling for 13.8 billion years, waiting for something capable of receiving it, waiting for us. Part 25. The architecture, how the universe organizes itself. The universe has a structure, not a random structure. not a uniform structure, a specific, hierarchical, beautiful structure that emerged without design, without direction from the simple action of gravity on the tiny density fluctuations of the early universe. At the smallest scales, stars, single objects, spheres of plasma, nuclear reactors burning hydrogen into helium, then star clusters, dozens to hundreds of thousands of stars gravitationally bound, then galaxies, hundreds of billions of stars with their associated gas and dust and dark matter, then galaxy groups, small collections of a few dozen galaxies, like our local group, then galaxy clusters, hundreds to thousands of galaxies, the largest gravitationally bound structures in the universe, then superclusters, collections of clusters and groups spanning hundreds of millions of light years, then the cosmic web itself, the grand structure of filaments and nodes and voids spanning the observable universe, each level nesting inside the next, each level shaped by the same force, gravity, working at every scale simultaneously. The cosmic web is one of the most beautiful structures in science. Not just visually, though, the simulations are extraordinary to look at, but conceptually, the idea that the entire large-scale structure of the observable universe, everything from galaxy clusters to the vast filaments connecting them, emerged from quantum fluctuations in the first moments of the Big Bang. Tiny, imperceptibly tiny, 1 part in 100,000, smaller than the variations you would measure in the temperature of a bathtub. Those fluctuations, amplified by gravity over 13.8 billion years, became everything. Every galaxy, every star, every planet, every living thing, everything has its ultimate origin in a quantum fluctuation, smaller than any scale we have a name for. The universe built itself from almost nothing to everything through the patient, relentless action of a single force. That is either the most remarkable thing I have ever understood, or the most remarkable thing anyone has ever understood. The filaments. The filaments of the cosmic web are not just structures. They are highways. Galaxies form along them, move along them, flow toward the dense nodes at their intersections. The filaments contain a diffuse, warm gas, the warm, hot intergalactic medium material that was never quite dense enough to collapse into galaxies, that was heated by the same processes that built the web, that sits between galaxies, in the threads, invisible to optical telescopes, but detectable in X-rays and through its absorption of light from distant quasars. The filaments are not empty. They are warm. They carry material from place to place. They connect the universe's neighborhoods, not with roads or paths, but with gravity, with the slow, inexorable pull of concentrated matter, drawing everything inward, drawing everything toward the nodes. The cosmic web is not static. It is evolving, growing. The clusters at the nodes are getting denser. The voids are getting emptier. The web is sharpening, becoming more defined as dark energy pushes the universe apart and gravity tries to pull it back together. Two forces, one cosmic, one local, in permanent tension. The structure of the universe is the visible record of that tension, stretched across 93 billion light years. In every direction, part 26, the planets of other stars, worlds without number. For most of human history, we did not know if other stars had planets. We suspected, we hoped, but we could not know. The stars are too far away, the planets too small, too faint, too close to the overwhelming glare of their parent star. For millennia, the question was unanswerable. And then in the 1990s, the answers started coming. The first confirmed exoplanet around the main sequence star was discovered in 1995. 51 Pegasi b, a gas giant, half the mass of Jupiter, orbiting its star in just 4.2 days, roasting in the stellar heat. Nothing like anything in our solar system. And yet, a planet, another world, around another star, the first confirmed, the door opened. Today, in the mid-2020s, we have confirmed more than 5,500 exoplanets, with thousands more candidates awaiting confirmation. And the data from the Kepler Space Telescope, which observed 150,000 stars simultaneously, watching for the tiny dimming that occurs when a planet crosses in front of its star, suggests something extraordinary. Almost every star has planets. Not most. Almost every. The average star in the Milky Way has at least one planet. Many have several. Our solar system, with its 8 planets and numerous smaller bodies, is not unusual. It is typical. The range of planets we have found is astonishing. Hot Jupiters, gas giants orbiting so close to their stars that they complete an orbit in days, their atmospheres blazing and evaporating. Super Earths, rocky planets larger than Earth but smaller than Neptune, the most common type of planet in the galaxy and a type not present in our own solar system, mini-Neptunes, planets with thick hydrogen envelopes, midway between Earth and Neptune, ocean worlds, planets that may be covered entirely in deep liquid water, lava worlds, rocky planets so close to their stars that their surfaces are covered in molten rock, rogue planets, worlds that have been ejected from their solar systems, wandering the galaxy without a star, pulsar planets, worlds orbiting the rapidly spinning, radiation blasting remnants of dead massive stars, and rare but real Earth-sized planets in the habitable zones of the stars, the places where liquid water could exist, where conditions might perhaps support life. The Kepler Space Telescope found, in its primary mission, that approximately 1 in 5 Sun-like stars has an Earth-sized planet in its habitable zone. 1 in 5. The Milky Way has roughly 100 billion Sun-like stars. 1 in 5 of those, 20 billion Earth-sized planets in habitable zones. In our galaxy alone, 20 billion worlds where the temperature might be right, where liquid water might exist, where the conditions for life might be present. Not all of them will have water. Not all of them will have atmospheres. Not all of them will have the right chemistry. But 20 billion is an enormous number. Even if only 1 in a million of those worlds has life, just a wild estimate that is 20,000 living worlds in our galaxy. And the Milky Way is one of 2 trillion galaxies. The mathematics of life in the universe are staggering. Whatever the answer to the Fermi paradox, whether we are alone or whether the universe is teeming with life, the scale of the possible is incomprehensible. The atmospheres, we are now beginning to read the atmospheres of other planets. When a planet transits its star, passes between us and the star, some of the starlight filters through the planet's atmosphere. Different molecules absorb different wavelengths. The pattern of absorption, the transmission spectrum, is a chemical fingerprint, the atmosphere of the planet, written in the light of its star. The James Webb Space Telescope has detected carbon dioxide, methane, water vapor, and sulfur dioxide in the atmospheres of exoplanets. Complex molecules, some of them associated with biological processes. Not proof of life, not even near proof, but the information is there. The atmospheres of distant worlds readable from here without going there, without sending a probe, just by analyzing the light. We are beginning to sniff the air of other worlds from 40 light years away. The question of life beyond Earth is no longer purely philosophical. It is becoming observational, doubly. In the next few decades, with the next generation of space telescopes, we may find what we are looking for or confirm the silence. Either answer changes everything. Part 27. The speed of everything. Nothing is standing still. Nothing in the universe is stationary. Not one thing. At every scale, everything is moving. The moon orbits the Earth at about 1 kilometer per second. The Earth orbits the sun at about 30 kilometers per second. The solar system orbits the center of the Milky Way at about 230 kilometers per second. The Milky Way moves within the local group at roughly 130 kilometers per second. The local group falls toward the Virgo cluster at roughly 300 kilometers per second. All of this flows toward the Great Attractor at roughly 600 kilometers per second. And the entire Laniakea supercluster, along with everything I've just described, moves through the universe relative to the cosmic microwave background at approximately 627 kilometers per second. All of those velocities, all happening simultaneously, all the time. You are, right now, moving at the sum of all these velocities relative to the CMB, not because you are doing anything, not because of any effort, simply by being inside a solar system that is inside a galaxy, that is inside a supercluster, that is inside the universe. The motion comes with the address. And yet, from here, everything appears still. The sky does not blur. The stars do not streak. The galaxies do not visibly shift, because everything around us is moving in roughly the same direction, at roughly the same speed. Relative to each other, the things we can see directly, the motion is almost imperceptible. It takes centuries of careful measurement to detect the proper motion of nearby stars, decades to map the motion of galaxies. Only the most advanced instruments can detect the bulk flow toward the Great Attractor. From inside the motion, the universe feels still. The same illusion you experience on a smoothly moving train. The world outside passes at speed. But inside the train, relative to the seat, relative to the other passengers, everything is calm. The universe is a very large train, and we have been on it our entire lives. Part 28. What makes Earth special? The unlikely planet in a universe of 2 trillion galaxies and 200 sextillion stars in a cosmos, 93 billion light years across the Earth, is a point. Less than a point, a mathematical abstraction, an infinitesimally small location. And yet, it may be one of the most unusual places in the universe, not because of its size. Earth is a small rocky planet, unremarkable in size, not because of its star. The sun is a completely average star, middle of the road in every parameter, not because of its position in the galaxy. The Orion Arm is a quiet backwater, not because of its age, 4.6 billion years. The universe is 13.8 billion years old. Earth is middle-aged. What may be unusual about Earth is the combination, the specific combination of factors that allowed life to arise and persist and become complex. The moon, our moon, is unusually large for a rocky planet of Earth's size. It formed from a catastrophic collision early in Earth's history, a Mars-sized body striking the proto-Earth, the debris coalescing into the moon. That large moon stabilizes Earth's axial tilt. Without it, the tilt would wander chaotically over millions of years, from near zero to near horizontal. The climate would be dramatically unstable, perhaps too unstable for complex life to persist. Jupiter, the giant planet, acts as a gravitational shield. Its enormous mass deflects many comets and asteroids that would otherwise impact the inner solar system. Life on Earth has benefited from this shield. Though the picture is more complicated than a simple protector, Jupiter also occasionally redirects objects into the inner solar system. But overall, the presence of a large outer planet may be one of the conditions that allowed complex life to develop without being regularly sterilized by mass extinction impacts. Plate tectonics. Earth is the only planet in the solar system known to have active plate tectonics. This geological system, the movement of crustal plates, the subduction of ocean floor, the uplift of mountains, serves a crucial function. It recycles carbon. Carbon dioxide is removed from the atmosphere by weathering, carried into the ocean, incorporated into seafloor sediment, subducted into the mantle, and released back into the atmosphere through volcanic activity. This carbon cycle, regulated by plate tectonics, is a thermostat, keeping the Earth's climate within a habitable range over geological time. Without it, carbon dioxide would either build up catastrophically as on Venus or deplete catastrophically as may have happened on Mars. With it, stability, a stable climate, persistent liquid water, 4 billion years of habitability. The distance from the Sun, Earth sits in the habitable zone, the region where liquid water can exist on the planetary surface. Not too hot, not too cold. The position is not perfectly optimized. Venus is just inside the habitable zone and has lost its water. Mars is just outside and is frozen. Earth is in the right place, not by design, by the specifics of how the solar system formed. And it has stayed in the right place even as the Sun has gradually brightened over 4.6 billion years because of the carbon cycle and the plate tectonics and the other feedbacks that regulate the climate. The habitable zone is not a guarantee. It is a starting condition. Life, once it arose, helped maintain the conditions for its own survival. By modifying the atmosphere, by drawing down carbon dioxide, by producing oxygen, by changing the reflectivity of the surface, the planet and the life on it have co-evolved, each shaping the other, for 4 billion years. The combination of all these factors, the right moon, the right giant outer planet, the right geology, the right orbital position, the right history, may be rare, not each factor individually, but all of them together in the right configuration, at the right time, for long enough to allow intelligence to arise. We do not know how rare. We do not have enough data. We have found the factors separately. Other planets have large moons. Other planetary systems have giants in the outer regions, but we do not know how often they all combine. And we especially do not know how often life arises. We have exactly one data point: Earth. A sample size of one is not statistics. It is a story, a remarkable, improbable, extraordinary story. But whether it is one story among many or the only story that has ever been told, we do not yet know. Part 29, the long silence, listening to the universe. We have been listening since 1960. 70 years of listening, the search for extraterrestrial intelligence. SETI, radio telescopes pointed at the sky, searching for patterns, for signals that could not be natural, for the unmistakable signature of technology. The universe produces natural radio signals. Pulsars, rapidly rotating neutron stars, emit regular pulses of radio waves. Regular enough that when the first one was discovered in 1967, the astronomers briefly called it LGM-1, Little Green Men 1. Before the natural explanation became clear, the galaxy is full of natural radio sources, synchrotron radiation from electrons spiraling in magnetic fields, the thermal emission of hot gas, the maser emission of molecular clouds. Separating a technological signal from all of this, finding the needle in a cosmic haystack, is the challenge. In 1977, a radio telescope at Ohio State University detected something, a narrowband signal lasting 72 seconds, from the direction of the constellation Sagittarius, at almost exactly the frequency predicted to be most likely for interstellar communication, the 2,1 Zentimeter hydrogen line, the most common frequency in the universe, the frequency that any technological civilization would know about. The astronomer who found it in the data printout circled it and wrote a single word in the margin: wow. The wow signal. It was never detected again. Dozens of subsequent observations of the same region of sky. Nothing. The signal remains unexplained. It may have been a natural source we haven't identified. It may have been terrestrial interference. It may have been an artifact of the detection system, or it may have been what it appeared to be, a narrowband signal from somewhere in the galaxy at the right frequency, at the right intensity, lasting just long enough to be noticed, never to return. We don't know. We may never know. The wow signal sits in the history of SETI as the single most interesting thing we have ever detected, and it is deeply, endlessly ambiguous. The silence continues, not because we haven't been listening, because nothing is answered, or because we haven't been listening in the right way, or at the right frequency, or with enough sensitivity, or because there's nothing to hear. The silence is the data, and the data is not yet sufficient to draw conclusions. In the next few decades, new instruments will transform the search. The Square Kilometre Array, a radio telescope being built across South Africa and Australia with a total collecting area of 1 square kilometer, will be the most sensitive radio telescope ever built. It will be able to detect the equivalent of airport radar from nearby stars, not just targeted transmissions, not just signals aimed at us. Leakage radiation, the accidental signals that civilization produces simply by existing. If any civilization within a few hundred light years is producing radio frequency signals the way we do, the SKA might detect them. Not certainly, but possibly within the lifetime of people alive today, the answer might come. And if it does, if we find even the faintest, most ambiguous signal, it will be the most significant event in the history of our species. Comparable to nothing. The discovery that we're not alone. Part 30. The pale blue dot. The view from outside. In 1990, as the Voyager 1 spacecraft was leaving the solar system 6 billion kilometers from Earth, astronomer Carl Sagan convinced NASA to turn the spacecraft's camera back, to take one last photograph of home. In the image that came back, Earth appears as a pale blue dot, barely visible, a fraction of a pixel, floating in a shaft of scattered sunlight against the black of space. Sagan wrote about it. He described the Earth as a mote of dust suspended in a sunbeam. He wrote about the rivers of blood spilled by all those generals and emperors so that they could become momentary masters of a fraction of a dot. He wrote about our posturings, our imagined self-importance, against the backdrop of a universe that doesn't notice. And he wrote gently, with love for the species he was describing, about our responsibility to deal more kindly with one another and to preserve and cherish the pale blue dot, the only home we've ever known. I have looked at that image many times. I have looked at it when the world felt large and important and urgent, when the concerns of the day felt overwhelming, when the distance between people felt insurmountable. And I have looked at the pale blue dot, one pixel in a universe 93 billion light years across, and something shifts, not into despair, not into nihilism, not into the feeling that nothing matters because everything is so small, into something else, something harder to name, a kind of tenderness for the dot, for the everything that has ever happened to our species that is compressed into that single point of light, every love story, every discovery, every birth, every grief, every piece of music ever written, every building ever constructed, every meal shared between friends, every moment of kindness between strangers, all of it on that dot in a universe that is mostly empty, in a galaxy that is mostly empty, on a planet that is against all probability alive. The pale blue dot is not evidence that we don't matter. It is evidence of how remarkable it is that we exist at all. That matter organized itself into something capable of photographing its own home from 6 billion kilometers away, of looking at the image and feeling something, of writing about it, of sharing the feeling across generations, of lying in the dark decades later and thinking about it. This is not insignificance. This is the most extraordinary thing we know of in the universe. A planet that knows what it is. A species that can be moved to tenderness by a photograph of its own home. From the outside, part 31, what the night teaches, the education of darkness. The night has always been a teacher. For all of human history, before electric light, before the orange glow of cities washing out the sky, the night sky was the most constant, most accessible, most spectacular thing a human being could look at. Every night, everywhere on Earth, the same stars, moving predictably, reliably, the first clock, the first calendar, the first map. The ancient Polynesians navigated the Pacific, the largest ocean on Earth, using the stars, without instruments, without compasses, without any technology beyond human perception and human memory. They memorized the paths of hundreds of stars, knew which stars rose over which islands, knew how the stars moved at different latitudes, knew the patterns of ocean swells and the flight paths of birds, and navigated with extraordinary precision across thousands of kilometers of open ocean, finding islands that appear as dots on modern maps, islands invisible from more than a few kilometers away. Found by reading the sky, the stars taught them to navigate. The night sky was practical, essential, life or death. The ancient Egyptians oriented their monuments to the stars. The pyramids aligned with extraordinary precision to true north, to specific stars. The Great Pyramid of Giza is oriented to within a fraction of a degree of true north, an achievement that required sophisticated astronomical observation, that required watching the sky for years, mapping the movement of stars, understanding the precession of the Earth's axis. The stars were not just beautiful to the ancient Egyptians, they were sacred. They were the homes of gods. They were the measure of time. The night sky organized their civilization. For the ancient Greeks, the night sky was a library, stories written in stars. Orion the hunter, Perseus and Andromeda, the bear and the little bear, the scorpion that killed Orion placed on the opposite side of the sky so they would never meet. The stories organized the sky, made it memorable, made its positions and movements legible. The constellations are not random. They are a mnemonic system, a way of encoding astronomical knowledge and narrative. So it could be remembered, passed down generation to generation. Across millennia, the night still teaches, if we let it, if we find a dark enough place, if we turn off the phone, if we just lie on our backs and look up, the same stars, the same galaxy, the same universe that all of those people looked at, every civilization, every generation, for as long as there have been human eyes to look. We are not separate from them. We are the current iteration, the latest generation of a species that has always looked up and wondered and tried to understand and found in the trying something that felt like meaning. Part 32, the language of the cosmos, mathematics as the grammar of reality. There is something remarkable about mathematics, something that has puzzled philosophers and scientists for centuries. It works not just as a tool for calculation, as a language for reality. The equations that describe the motion of planets, the equations that describe the behavior of light, the equations that describe the structure of atoms, the equations that describe the curvature of space-time. All of them, mathematics, human-invented abstract structures that turn out to describe with extraordinary precision the behavior of the physical universe. Eugene Wigner, a physicist who won the Nobel Prize in 1963, wrote an essay called The Unreasonable Effectiveness of Mathematics in the Natural Sciences. The title says it all. Mathematics is unreasonably effective. It works better than it should. It reaches further than it has any right to. Mathematicians often develop structures for purely aesthetic reasons, for the beauty of the mathematics itself, without any reference to physical reality. And then decades or centuries later, physicists discover that the physical world is described by exactly those structures. Non-Euclidean geometry, developed in the 19th century as a mathematical curiosity, essential for Einstein's general relativity in the 20th century. Group theory, developed to understand symmetries in mathematics. Now, the language of particle physics, complex numbers, invented as a mathematical convenience fundamental to quantum mechanics. The universe speaks mathematics, or rather mathematics, somehow, is the grammar of the universe. And we invented mathematics and found that the grammar we invented matches the grammar of reality. That is either a profound coincidence or a profound clue about the nature of both mind and universe. When I think about mathematics, when I think about the fact that the equations describing the expansion of the universe were written by Albert Einstein in 1915, before anyone knew the universe was expanding, and that those equations predicted the expansion that was not discovered until 1929, I feel something, not quite wonder, not quite reverence, something in between. The sense that the universe has a structure deeper than its surface, a mathematical structure that our minds, also products of the universe, can access. Not completely, not yet, but partially. We are the universe understanding its own grammar, imperfectly, in progress, but trying. Part 33, the astronaut's planet, home seen from outside. There have been, as of 2024, a little over 600 people who have been to space. Not to other planets, not to other star systems, just to space, a few hundred kilometers above the surface. A distance that, on the scale of the observable universe, is essentially zero. But something happens when you go there. When you look back, when you see the Earth not in a photograph, not in a video, but with your own eyes, through a window, the actual planet hanging in the actual dark, something changes permanently. Astronauts describe it consistently. The thinness of the atmosphere, how fragile it looks, how the blue line at the edge of the planet, the atmosphere is so thin, thinner than the skin of an apple, thinner than you can believe. The layer of gas that contains everything, all the weather, all the life, all the history, everything that has ever happened on Earth, in that thin blue line. They describe the absence of borders. From space, the political boundaries that define countries, the lines that human beings have fought and died over for millennia are invisible. The land is just land. The ocean is just ocean. The atmosphere is just one atmosphere, shared, not divided. One system, belonging to no one, belonging to everything. And they describe the emotion unexpectedly. Many astronauts, engineers, pilots, scientists, practical people, not given to public expressions of sentiment, and yet they describe weeping at the window, unable to look at the Earth without being overwhelmed, not with sadness, with something they struggle to name. Love, some say, gratitude, connection, the sense that the divisions between people are simply wrong, not politically wrong, physically wrong, inconsistent with the reality of what the planet actually is. One thing, whole, alone, precious, in a very large, dark, we cannot all go to space. Not yet, perhaps not ever, but we can try to see what they see, not through a window, through understanding, through the knowledge of what the universe actually looks like from the outside, through the pale blue dot, through the Hubble Deep Field, through the understanding that the Earth, for all its history, for all its conflicts, for all its diversity, is a single point of light in a universe of 2 trillion galaxies. And that single point of light is the only place in the universe where, as far as we know, anyone is home. Part 34, the final numbers, what we know for certain. Let me give you the numbers, not as things to memorize, not as things to feel overwhelmed by, but as a summary, a map of everything we have traveled through tonight. The Earth, 12,740, 2 kilometers in diameter. The Moon's distance from Earth, 384,400 kilometers. The Sun's distance from Earth, 149.6 million kilometers. The nearest star, Proxima Centauri, 4.24 light years. The Milky Way, 100,000 light years across. The local group, 10 million light years across. The Virgo supercluster, 110 million light years across. Laniakea, 520 million light years across. The observable universe, 93 billion light years across. Number of stars in the Milky Way, 400 billion. Number of galaxies in the observable universe, 2 trillion. Number of stars in the observable universe, approximately 2 times 10, 23. 200 sextillion. Age of the universe, 13.8 billion years. Age of the Milky Way, 13.6 billion years. Age of the Earth, 4.54 billion years. Age of life on Earth, 3.7 billion years. Age of complex multicellular life, to 600 million years. Age of Homo sapiens, to 300,000 years. Age of modern civilization to 10,000 years. Age of modern science to 400 years. These numbers are not approximations, not guesses. They are the result of centuries of careful observation, of generations of scientists looking at the sky, building instruments, developing mathematics, testing ideas against reality, refining, revising, always getting closer. They are the best answer we have right now to the question, what is the universe? How big is it? How old is it? How did it come to be? What is it made of? Where is it going? Not final answers. Science does not offer final answers. It offers better and better approximations, closer and closer approaches to truth. And these numbers, these specific, hard-won, carefully verified numbers are where we are right now. In the 13.8 billionth year of the universe, in the 454 billionth year of the Earth, in the 300,000th year of our species, in the 400th year of systematic observation of the sky. This is how much we know. After 400 years of trying, final section, the long breath coming all the way home, and so we arrive at the end, not of the universe, not of the questions, just of tonight. We began with a number I wasn't ready to give you. I wanted you to have the feeling first. The feeling of what it means to try to comprehend something this large. And then the number, the ratio, 930, 0002, the observable universe to the Milky Way. Have you felt it? Not understood. Felt. The way you feel something in your chest when music is very beautiful. The way you feel something behind your eyes when a landscape is very vast. The way something shifts quietly without drama when a mind tries to hold something much larger than itself. That feeling, because that feeling is not nothing. That feeling is the mind reaching, extending itself toward the actual scale of reality, trying to be large enough to contain what is there. Never quite succeeding, but trying. The trying itself is extraordinary. The attempt to feel the universe truly, to not just know the numbers, but to be moved by them, is one of the most human things there is. The universe is 930,000 Milky Ways across. The Milky Way contains us, the part of the universe that knows how big it is, the part that measures, the part that wonders, the part that in the dark, at the edge of sleep, lies still and tries to feel the actual scale of the place it is in and finds it beautiful. Let the breath slow now, all the way down, the long breath, the breath that has been there this whole time, through all the numbers, through all the galaxies, through the Big Bang and the CMB and the Hubble Deep Field and the pale blue dot. The breath was here, simple, steady, ancien, the same mechanism that has been operating in living things for hundreds of millions of years. Oxygen in, carbon dioxide out, the chemistry of the stars in you, right now, in the dark. The universe is 93 billion light years across. The room you're in is maybe a few meters. Both are real, both are yours. The small room, the enormous universe, both at the same time. You are always both. The speck and the one who knows it is a speck. Both simultaneously, without contradiction. Let the scales nest. Room inside building, building inside city, city inside country, country inside continent, continent inside planet, planet inside solar system inside galaxy, galaxy inside local group inside Laniakea, Laniakea inside the observable universe. All of it inside you, inside your awareness, right now, in this room, at this moment, all of it held in one mind, one temporary, precious, extraordinary mind that is resting now, that deserves to rest. The galaxies don't need you to watch them. The stars don't need your attention to burn. The universe has been doing this for 13.8 billion years without any help. It will continue tonight and every night. The Andromeda Galaxy moving toward us at 110 kilometers per second. The Great Attractor pulling at 600. The universe expanding in every direction at once. All of it. Without effort, without rest. Just physics. Just the laws. Working as they always have. And you, here, in the small room, inside the enormous universe, can rest, should rest. The universe does not require your consciousness to continue. It only requires yours to be noticed. And tonight you have noticed, you have tried to feel the scale. You have held the numbers. You have traveled from here to the edge of everything we can see and back, and that is enough. That is more than enough. Close your eyes. Let the numbers go. Let the galaxies spin without your attention. Let the filaments of the cosmic web hold their shape without you. Let the void be void. Let the stars burn. Let the universe expand. Let Andromeda approach. Let the CMB fill the sky from every direction. Let it all continue, as it will, as it must, and here, in this room, in this moment, let the breath be what it is. Simple, old, connected to everything, to every living thing that has ever breathed on this planet, to the oxygen made in stars, to the carbon that passed through 1,000 other lives before arriving in yours. You are not separate from any of it. You are the universe, resting, knowing it is vast, and finding that vast enough, quietly, beautifully, enough. Sleep now. The universe is exactly the right size, and you are exactly where you are supposed to be. Inside it, part of it, known by no one, and knowing everything you know, which is already extraordinary, which has always been extraordinary. Sleep.